Hello everyone. In this lecture today we are going to talk about multiple access protocols. So there are two types of links, and multiple access protocol allow multiple users to access the same link. So the two types of links are point-to-point links, or there are broadcast links. Now point-to-point links are basically a direct wire that connects the host to the direct wire between two hosts. For example, the dial-up connection that you have, a point-to-point Ethernet cable running between two hosts or two nodes, that is a kind of a point-to-point link. A broadcast medium is something that's shared. The one that comes to mind is the wireless medium. For example, a wireless LAN that you use is an example of a broadcast medium. That does not mean that Ethernet cannot be broadcast. The old-fashioned Ethernet is also a broadcast medium. And we'll look at, in this lecture today, we'll talk about multiple access links and the protocols in these. Now, what happens when multiple users share a broadcast medium? So when two or more users try to simultaneously transmit across a shared medium, what happens is collisions can occur. Now, let's consider this example of a cocktail party. In a cocktail party, if everybody is speaking at the same time, you cannot understand what the other person is speaking at all. That's because there is collision, because they're both all of you are all of the participants of the party are speaking at the same time. To allow you to be able to clearly understand what the other person is speaking, you need only one person to speak at a time. So in the case of a computer network, there will be collision if two or more nodes, like if a node receives transmissions from two or more nodes at the same time. Now, the multiple access protocols are kind of a distributed protocol that basically every node runs by itself and determines whether it should transmit at a particular point or not. So that is the essence of a multiple access protocol. It allows users to share the broadcast channel and tries to make sure that collisions are minimized, or in some cases there are no collisions at all. Okay, so let's first talk about an ideal multiple access protocol. Say a broadcast channel has R bits per second, that's the rate of a broadcast channel. If there are M users, you're going to want to use the channel, the maximum that on an average every user can get is R over M. Because let's assume that every user has something to transmit. So what you could do is every user is given access to the channel for some length of time, and then the user transmits over that channel, and then other users take turns to transmit at the same time. So on an average, every user takes R over time, R over M. So the advantages of this kind of simple protocol is that it's fully decentralized. There's no coordination between the nodes. There's no synchronization of clocks. They know when they have to transmit. It's very, very simple. But as you might have already realized, this is an ideal multiple access protocol, and so it's not going to work well in the real world. One easy example of that for that is there are clocks. In the real world, you use clocks, and they need to be synchronized, and synchronization is a hard problem. So we will talk about medium access protocols, or MAC protocols, in three broad classes. One is channel partitioning protocols. Then we'll talk about random access protocols, and then we will talk about a protocol in which nodes take turns to transmit. So we just have this taking turns kind of protocol. So we begin today's lecture by first talking about channel partitioning protocol. So in a channel partitioning protocol, the channel, by channel I mean that is the broadcast channel that's used by the multiple nodes, is divided into smaller pieces, and each piece is given to a node. Now what I mean by piece? A piece can be either a time slot, or it can be can be in terms of frequency. Okay, so let's look at the first kind of channel partitioning protocol, that is TDMA, which stands for time division multiple access. That's what TDMA stands for. In TDMA, what you do is you divide time into small slots, and then each of these slots is given to a user. So let's assume that there are six nodes that are connected in a LAN, and so you divide time into small slots. All the slots are of equal length, and each slot is given to a user. So what you can see is the first slot is given to user 1, second slot to user 2, third to 3, and so on. And there are 6 slots. In this figure here, you can see that, and the first user transmits, then there is nothing that the second user may not have anything to transmit, then the third user has something to transmit, the fourth user also has something. The fifth and sixth do not have anything to transmit. And once this, like all users have been given an opportunity to transmit, then one transmits again. This is going to work well if every user has something to transmit. But say all users will not have something to transmit at the same time. As here, as in this example, 2, 5, and 6 do not have anything to transmit. So those slots go empty. So it's very simple here that this is only operating as 50% efficiency because 50% of the slots are vacant. So that is a channel partitioning protocol or time division. And what we looked at is time division multiple access. Now, you could also think of dividing frequency into slots. So what you have is the entire range of this frequency spectrum that is allocated is divided into a number of bands. Each band is given to a particular user. So here you have once again we're looking at the same example where there are 6 nodes in a wireless LAN, in a LAN, and each node has been given a particular frequency band. So you can see that the first frequency band is given to user 1, the second to user 2, and so on. Once again, because only 1, 3, and 4 have anything to transmit, they transmit. The only difference is that they have a smaller frequency spectrum to transmit because here frequency has been divided instead of time, and they could transmit for the whole duration of time during those different frequency bands that have been allocated to them. So this is frequency division multiple access, or FDMA. This is the second type of channel partitioning protocol. Now, so channel partitioning protocols are pretty simple, where you just divide the channel and then allocate those resources to the different users. Now, the other kind of protocol that we look at is random access protocol. And why you might think of a random access protocol is that not all users have something to transmit, right? So in the previous example, 2, 5, and 6 had nothing to transmit. So in a random access protocol, when a node has something to transmit, it could get access to the channel and then transmit it. The good part about this is what's going to happen, there's no synchronization. There need not be too much synchronization among the users, right? Because they're going to take a random amount of time, they're going to decide, and then you're going to transmit. And like in an FDMA or a TDMA, where the channel is divided and this into slots, and this information has to be communicated to the users as to which user has to use which slot. Now, with this brief understanding of what random access MAC protocols do is, we'll look at 3 examples: Aloha, Slotted Aloha, and CSMA CD. Now, you could have already realized that if 2 users are just deciding among themselves as to when they want to transmit, it's likely that they could start transmitting at the same time, and hence there can be collisions. In an FDMA or a TDMA, we avoided that collision by making sure that nodes are given specific slots at which they could transmit, which is not the case in case of random access protocols, where they randomly decide when they have to transmit. So let's look at the first protocol, that is LAN Aloha. So here we make a few assumptions which will make it much simpler to analyze. We assume that all link layer frames are of the same size. This is a reasonable assumption. What we again do is time is divided into equal size slots. So time is once again divided into slots, and then nodes can begin transmitting only at the beginning of a time slot. Okay? And they cannot start transmitting in the middle of a time slot. And if 2 nodes transmit in the same time slot, then a collision is going to occur. So here, the time is divided into slots, but slots are not allocated to the different users as in TDMA or as in TDMA. Here, time is divided into slots, and user could randomly decide if they want to transmit in a time slot or not. Okay. Now, say a node picks a time slot to transmit. What happens is it transmits, and if no other node is transmitting, its transmission is successful. And then in the next time slot, if it has further data to send, it could use that time slot to send its data. But say it was transmitting in a time slot, and then another node also started transmitting in the same time slot. What happens is the two transmissions are going to collide. Now, if both nodes decide to transmit once again in the subsequent time slot, they're again going to cause this kind of collision. So, if there is a collision, a node will not transmit for sure in the next time slot. It is going to transmit with some probability p in the next time slot. This is going to give the transmissions some a chance of succeeding. Okay, so let's look at this example. An example will make all the points very clear. So say what's happening is in the first time, node 1, 2, and 3, there are 3 nodes in this LAN, and all of them want to have some data to transmit. What happens is node 1, 2, and 3 all transmit in the first time slot. Then there's a collision. So with some probability, every node has a chance of transmitting in the second time slot, in the next time slot, which is this E. It's like a coin toss, and say none of the nodes choose to transmit in this time slot. Then again in the next time slot, with some probability, they're again going to try and transmit. 3 once again decides not to transmit. 1 and 2 decide to transmit. What happens is there's once again a collision, and then in the next time slot, 1 and 3 do not choose to transmit. 2 transmits. The packet is successful. Now, if 2 had further data to transmit, it would have transmitted in the next time slot, but 2 has no other data to transmit. So its 2 is done with its transmission. Now, in this time slot, 1 and 3 choose not to transmit again. And then what happens is both choose to transmit again at the same time. So there is another collision. Then there is in this E here, 1 and 3 again choose not to transmit. Then 1 chooses to transmit, 3 does not choose to transmit in S. So the transmission is successful, and in the subsequent time slot, 3 chooses to transmit, and that transmission is successful as well. So one of the biggest advantages of this is that if there is only a single node which has some data to transmit, then it could utilize the channel fully. Like it could just keep transmitting, there are going to be no collisions, and you could use the channel fully. The other thing is it's very simple and it's purely decentralized. There is no central authority telling nodes when they have to transmit or or how they have to transmit. The only thing is that there is a synchronization issue, that all nodes need to know the beginning of the time slots, because transmission is beginning at the beginning of a time slot. But the cons, as you've seen, is there are lots of collisions. And we assume that that nodes will be able to detect these kind of collisions as well. So the number of collisions that occur here is really high. Now, if you do a lot of analysis, and I'm not going to go into the math, what I want you to take out of this is what is the efficiency of this kind of slotted Aloha. So all the analysis that's going to tells you is there is only going to be useful transmission for approximately 37% of the time. So even if nodes have more data to transmit, on average, only 37% of the transmissions are going to be successful. The remaining transmissions are all going to result in collisions, and they are going to be wasted. So slotted Aloha is not the best protocol that one can think of, because it is a very low efficiency. But then it has got this advantage of being simple. The only one of the biggest disadvantages that it has is the clocks of the users have to be synchronized. And that makes it something very difficult to implement in practice. So let's take one step back and think about an unslotted Aloha, where users, whenever they have a packet, they can choose to transmit. Okay, so it's simpler than Aloha. It's the simplest protocol that I could think of. So there is no notion of time divided into slots. So whenever a frame arrives, user can just decide whether they want to transmit or not. And if there is no collision, and they have more data to transmit, they can continue to transmit. Otherwise, once again, if there is a collision, every user with some probability does not transmit for some length of time, and then they transmit again. It's similar to Aloha. Similar to slotted Aloha. The only difference is that there's no notion of time slot. Okay. And now let's understand how well a pure Aloha protocol works. The thing is, it works only half as well as the slotted Aloha. So it has an efficiency of 18%. That is, only 18% of all transmissions will not result in collisions. The remaining transmissions will all result in collisions. So it is a performance even worse than slotted Aloha. And the main reason for this loss of performance, without going to the math, is that in slotted Aloha, their users could only start transmitting at the beginning of a time slot. In pure Aloha, they could transmit whenever they want. So that is one of the biggest disadvantages of the pure Aloha scheme. So the pure Aloha is the easiest to implement in practice because it's simple, there's no synchronization, it's completely decentralized. But such a protocol gives only 18% efficiency. The reason why Aloha and slotted Aloha are really important is that it tells you, if you design a very simple protocol, how well are you going to work. So that is why we teach slotted Aloha and pure Aloha. Having given you a basic idea of these random access protocols, we'll go into something a little bit more sophisticated, something that's used. That is actually CSMA, which is Carrier Sense Multiple Access. Now, what it does is, if it senses if the channel is busy before it transmits. If the channel is busy, it defers its transmission. It makes sense, right? Say if you have something to say, and if somebody else is speaking, it's courtesy not to interrupt others. Let that person complete what he or she has to say, and then you can speak. So that is the same principle that we use in a carrier sense multiple access protocols. You sense the channel, and if it's idle, you can transmit. Otherwise, you just defer your transmission till the ongoing transmission finishes. Because if you transmit, then both packets are going to collide, and then it's going to be wasteful transmissions. Okay, but does CSMA make sure that collisions do not occur? Because what CSMA is trying to do is, when there is a transmission going on, it does not transmit at the same time. But this simple principle does not make sure that collisions will not occur. The main reason for that is the signals take a finite amount of time to propagate. So let's consider this simple example here. So at time t equal to 0, the second node here starts transmitting its frame or packet. What happens is, at time t equal to t1, this transmission has still not reached node 4, or this node out here, because it's still propagating onto the wire. This node here senses the channel, it sees that the channel is idle, and then it starts transmitting. What's going to happen is, it's going to start transmitting, and then both these packets are going to collide in the air. These packets collide in the air, and at some time after T1, then there is, though both nodes tried to do carrier sense multiple access, the collisions collided in the air, and then none of the transmissions were successful. So the important point to take away from CSMA is that CSMA tries, like, though you do carrier sense, you can still have collisions. Okay, so the next natural step is, can you detect collisions? So the easiest thing is, because in the previous slide we realized that if a collision occurred, if you could detect collisions, you could just avoid the transmission that's going on. If you avoid the transmission that's going on, then you can reduce channel wastage, because anyway the two packets have collided, and what's going to happen is that transmission is wasteful. So in CD, What I mean is CSMA CD, career sense multiple access collision detection. What happens is you you stop a conversation or you stop transmission when you see that a collision is on. It's basically in the human analogy is a polite conversation. Okay, so let's look at the same example with a collision detection. What happens is you can see here that at this point in time, so the collision occurred here at this point in time. However, none of the nodes realized that there was a collision because the signal had still not propagated. Sometime later, this node here realizes that there has been a collision. Okay, this is the time. This node here realizes at this point in time here that a collision has occurred. So it can abort its transmission at that time because no matter even if it transmits its packet, that is not going to be useful. Some additional time later, that is this time here, this node realizes that there has been a collision, with the result that even that node can stop transmitting. Now, if these two nodes stop transmitting and stop transmitting, they do not need to waste the additional bandwidth that they're wasting because anyway the transmission is not going to be successful. So that is the principle behind CSMA CD or carrier sense multiple access collision detection. So we started from Aloha and we looked at its two variants, the pure Aloha and the slotted Aloha. Then we went to CSMA, that carrier sense multiple access. And then we went to carrier sense multiple access collision detection. And CSMA CD is the protocol that is used in the Ethernet. So in an Ethernet, it is CSMA CD that is used, and everything that I told described to you about CSMA CD is used. The only additional thing is when does a node start retransmitting again? So there is a collision that was detected. Now the node the node can abort its transmission, but then it wants to send its packet or its frame. So the principle that's aborted is binary backoff or exponential backoff. So the way to look at it is when say there have been M collisions. So a node has tried to transmit, and every time it has tried to transmit, it has experienced a collision. That is, it has tried to transmit M times, and all the M times there has been a collision. M can be any number, like from 1, 2, 3, so on. What it does is it then picks a number between 0 and 2 to the m minus 1. So say if m is 3, then it's going to pick a number between 0 and 2 to the power of 3 is 8, minus 1, that is 7. So it's going to pick a number between 0 and 7. And say it picks a number, say 5. So it waits for 5 units of time before it transmits. So more collisions that a node experiences, it's the chance that there's a higher chance it has to wait for a longer length of time before it transmits. So it picks a number at random in this set. Okay. Now, the reason why this randomization helps is, say there are two nodes who are trying to transmit and they collide. They collide the first time, then they collide the second time, then they can collide the third time. Now, after the third time, both are going to pick numbers from, say, 0 to 7, right? Say some node picks 1, the other node picks 5. Then there's no way that transmissions are going to collide because the transmissions are going to take place at different times, and both are going to be successful. To randomization, make sure that two nodes do not, after a collision, they do not start transmitting at the same time. This is a very important concept, and I would really like you to appreciate this, because this is going to be really important for your exams as well. So the efficiency of CSMA CD is much better than Aloha, and that's the only thing that I want to say. And it's pretty simple. It's not as simple as Aloha, but it's very simple, and it's also decentralized, and also does not require any kind of synchronization between the nodes. So this is a formula, and I don't want you to remember this. So all I really want to know is its performance is much better than slotted Aloha, and that's the protocol that's used in the Ethernet today. Now, we looked at first we looked at channel partitioning protocols, TDMA and FDMA. Then what we did is we looked at random access protocols, and now we're going to look at taking turns protocols. This taking turns protocols tries to get the best of both worlds. So it tries to combine channel partitioning as well as random access protocols. Okay, so how does it work? So let's look at the simplest cases, polling. So here, this configuration is called a master safe configuration, where there's one node which is designated as a master, all the other nodes are designated as slaves. The master basically asks the slaves, and the slaves are quote unquote dumb, whether they want to transmit. Now, if some nodes want to, so it polls, and then that node, basically here it polled node 1, and that node sent the data. Then it polls the other, it does not poll the second node, because the second node may not have any data transmit. It then polls the third node, and then the third node says, I want to transmit, so it had this transmitted the data. Okay, so taking turns in case of polling is much better, because it invites and makes sure that only nodes which have to transmit can actually transmit at the same time. One of the biggest issues with taking turns protocol is like there is a master. So if the master somehow crashes, say this node crashes, so the slaves have no way to determine who should transmit. So that is a single point of failure. The other thing is, though it's better than TDMA in the sense that you don't have wasted slots, there is still an overhead. The master has to poll the different nodes here and then determine which nodes should be given access to transmit. I'm sorry about that. So having described that the polling protocol, we'll now go into token passing. So token passing is another MAC protocol in which the different nodes pass tokens and determine who should transmit. So here what happens is this node has the token. So whichever node has the token has the chance to transmit, and once it has transmitted, it passes the token. Any other node which has some data to transmit, it is going to hold the token. So here this node released the token, it went to this node. This node has nothing to send. So what it does, it releases the token. The third node here grabs the token one more time, but it has some data to transmit. So what it does is it sends the data. In this case, the data just went around in a circle. After it has done transmitting the data, it's going to release the token, and then any other node which wants to transmit can grab hold of that token. Okay. So this combines both random access and channel partitioning protocols, as you can see, because every node basically relies on the token to determine who has to transmit. So with that, we come to a discussion of the different MAC protocols. Today we talked about different channel partitioning protocols, that is TDMA, that is time division multiple access, and frequency division multiple access. We also talked about the random access protocols such as Aloha and Slotted Aloha. Then we looked at CSMA, which is carrier sense multiple access, and CSMA CD, which is carrier sense multiple access collision detection. We'll not have time in this course, but there's another protocol called carrier sense multiple access collision avoidance, that is CSMA CD, which is used in a wireless LAN. After completing random access and channel partitioning, we looked at taking turns protocols, which combine the best of both worlds, and we looked at polling and the token passing algorithm. With that, I'll conclude this lecture. Thank you.